Hello everyone, I'm Matthew and this is my final video presentation for Robotics Lab 3. Over the course of this lab, I explore four key areas. Those are tiny ammo, edge devices, prompt engineering, and computer vision. Each topic opens the door to a different piece of the AI and robotics world. In this video, I will explain what each concept means in my own words, walk through the hands-on activities I completed in class, and reflect on how these technologies are already shaping the real world and how I might use them in future. The first one is the tiny ML. The tiny ML stands for Tiny Machine Learning, and it refers to the process of running machine learning models on extremely small hardware like microcontrollers with very limited memory and processing power. That's the tiny ML. The main idea is to keep the computation on the device itself rather than sending data to the cloud. This reduces latency, saves power, and keeps data local, which is also better for privacy. In the class, I use an Arduino Nano 33BLE Sense, which has built-in sensors like an accelerometer. I performed three simple hand gestures, left, right, and up, and recorded the sensor data from the accelerometer. After collecting the data, I uploaded it to a platform called Edge Impulse, which is designed for tiny ML projects. I trained a classification model that could recognize the three gestures, then apply the model directly back onto the nanobots. The result? A smart device that could detect my hand gesture in real time without needing to connect to the internet or a more powerful computer. That's the result. This project took me to the full pipeline from gathering raw sensor data to training and validating a model to deploying it onto a device with tight hardware constraints. In the real world, TinyML is being used in a lot of emerging applications, whether it's the response to your movement, smart home devices that detect environmental changes, industrial tools that can predict equipment failures early based on sensor patterns. Even wildlife monitoring uses tiny ML like small solar power devices that can classify animal sounds deep in remote forests. It's powerful but lightweight. Let me talk about the second one now. The second one is edge devices. Edge devices are smart systems that process data locally rather than sending it to a central server or cloud platform. This is especially important in robotics where immediate responses are needed and any delay could cause a problem. In the lab, like when I applied the trained tiny ML model onto the nanobot, it essentially became an edge device. It didn't need the internet, it simply took real-time sensor readings, ran them through the model, and output the result all instantly. This helped me see how important low latency computing is in real world systems. In robotics, for instance, if a robot needs to stop to avoid hitting something, it can afford to wait for a server to respond. It needs to react immediately. Some other examples of edge devices in real life include like smart security cameras that recognize faces or motion, smart speakers that process your voice locally for a faster response, industrial robots that detect anomalies or changes in real time. Another benefit of edge computing is energy efficiency. Since data doesn't need to be constantly transmitted, it saves power, which is critical in battery powered devices. It also reduces bandwidth costs. This session made me realize that edge computing is not just a cool concept, it's a foundation for making AI practical in everyday objects. So let's talk about the third one, the prompt engineering. Prompt engineering is a newer scale, but it is becoming increasingly important as we work more with large language models like ChatGPT. It's not just about asking questions, it's about how you frame those questions to get the best possible answers. During this part of the course, I experimented with different types of prompts, like general prompts like explain machine learning, or like specific ones like summarize how a neural network processes impulses, or maybe like a multi-step prompts where I ask for outlines, examples, or analogies. What I noticed is that small changes in the wording made a big difference in the output. The more precise and well structured the prompts, the more accurate and useful the response. This showed me that working with AI isn't just about understanding the model, it's also about communicating effectively with it. In the real world applications, prompt engineering can be seen in like AI writing tools that help generate articles or reports, or customer service chatbots that respond based on specific phrasing, or also maybe like a programming tools like a GitHub Copilot, and maybe which generates code based on your instructions, of course. And this experience also gave me ideas for future projects, like using prompt chains to automate research tasks or summarize large amounts of sensors data from a robot. I think prompt engineering is underrated but essential skill for anyone working with AI tools, and it's something I will keep practicing. The last one, but not the least, computer vision. Computer vision is the field of AI that allows computers to understand visual information, whether it is images, videos, or real-time camera feeds. In the lab, I work with OpenCV and use a pre-trained mobile net model to detect objects from a webcam. I was able to identify everyday items like phones, bottles, or pens, or other things as well. I also play with lightning and the angles to see how those affect the predictions, and yeah, those factors definitely did. What made this part really engaging was seeing the feedback live on screen. The model wasn't perfect, but seeing it react to different objects in real time made it feel like the computer was singing for the first time. In real world terms, computer vision is used everywhere in autonomous vehicles to detect obstacles, lanes, and traffic signs, and in smart checkout systems that track what you take from shelves. Also in manufacturing, where robots use vision to inspect products for quality control. Computer vision can also be used for accessibility, like apps that help visually impaired users by identifying objects or reading signs aloud. I think what I enjoyed most was how visual and interactive this topic was. I feel like the AI wasn't just working in the background; it was part of the environment. So, looking back on the Robotics Lab 3, I can say it gives me one of the most well-rounded hands-on experiences with AI and robotics that I have had so far. Like each topic, Tiny Ammo, as devices, pro engineering and computer vision taught me something different. But what really stood out was how they fit together. Like imagine a future device that can detect gesture using a small sensor with tiny ammo, process the gesture locally and instantly as device, respond to natural language instructions, which is prompt engineering, and understand what's in front of it using a camera is a computer vision. Combine all of them. That's not science fiction, it does a smart system that I could start building with the tools and knowledge I gained from this course. As I move forward, I plan to use those skills in personal and academic projects. I want to try building a device that uses both gesture recognition and visual tracking, maybe even voice control to create a more natural human computer interaction experience. So overall, Robotics Lab 3 didn't just teach me how to use tools, it gave me a clear vision of how modern AI fits into the physical world. And I am really excited to keep building from here. Thanks again for watching, and I hope you enjoy this final reflection. Thank you.